Why mathematicians call certain numbers perfect? Numbers just look like ordinary symbols. 6, 28, 496. But when we take a closer look, we find that some of them behave in a very unusual way. They balance themselves so beautifully that for thousands of years, mathematicians have described them as perfect. Numbers like this are extremely rare. Out of the first 100 numbers, only two, 6 and 28, make the cut. And as numbers grow larger, they become even harder to find. Yet, despite their rarity, perfect numbers have fascinated mathematicians for over 2,000 years, connecting simple arithmetic to deep theories that are still being studied today. So, why are some numbers so perfect, and what makes them stand out from all the rest? That's exactly what we're going to explore in this video. So, what exactly is a perfect number? By definition, a number is called perfect if it is equal to the sum of its proper divisors. Proper divisors are all the positive divisors of a number, except the number itself. Let's start with the smallest example. 6, the divisors of 6 are 1, 2, 3, and 6. If we exclude 6, the proper divisors are 1, 2, and 3. Now, add them up. 1 plus 2 plus 3 equals 6. The total is exactly equal to the number itself, which makes 6 the very first perfect number. The next one is 28. The divisors of 28 are 1, 2, 4, 7, 14, and 28. Ignoring the number itself, we add 1 plus 2 plus 4 plus 7 plus 14 equals 28. Again, the sum matches the number perfectly. Notice how unusual this is. Take a number like 10. Its divisors are 1, 2, 5, and 10. Add the proper divisors and you get 1 plus 2 plus 5 equals 8, which is less than 10. Such numbers are called deficient. On the other hand, 12 has divisors 1, 2, 3, 4, 6, and 12. Add the proper ones. 1 plus 2 plus 3 plus 4 plus 6 equals 16, which is greater than 12. That kind of number is called abundant. So perfect numbers sit in a special category, balanced exactly in the middle, neither too small nor too large compared to their divisors. That's why they earned the name perfect. Once we move past 6 and 28, perfect numbers start to grow quickly. The third perfect number is 496, and the fourth is 8,128. From there, they become enormous. The next few have thousands, even millions of digits. But even as they grow, perfect numbers follow some fascinating patterns. First, notice their endings. Every perfect number after 6 ends in either a 6 or an 8. So, 28 ends in 8, 496 ends in 6, 8,128 ends in 8, and this alternating pattern continues. This isn't a coincidence. It's built into the way these numbers are formed. Second, they also appear in geometry. Take 28, for example. It's a triangular number. If you stack objects in a triangle, the seventh triangular arrangement contains exactly 28 objects. So perfect numbers often appear in shapes and arrangements, not just in pure arithmetic. Third, their structure in binary is also elegant. When written in base 2, perfect numbers look like a block of ones followed by the same number of zeros. For instance, 28 in binary is 11100 and 496 is 111110000. It's as if the numbers are perfectly mirrored between ones and zeros. And finally, they even show up in other surprising ways. For example, 28 can also be written as the sum of cubes. 28 equals 1 cubed plus 3 cubed. These little coincidences make perfect numbers stand out as not just mathematically balanced, but also aesthetically beautiful. Perfect numbers aren't a modern discovery. They've been known since ancient Greece more than 2,000 years ago. The first major mention comes from Euclid. Around 300 BC, in his famous book Elements, Euclid showed that perfect numbers can be generated from a special formula. If 2 to the power of p minus 1 is a prime number, then multiplying it by 2 to the power of p minus 1 gives a perfect number. For example, when p equals 2, 2 to the power of 2 minus 1 equals 3, which is prime. Multiply it by 2 to the power of 1, which equals 2, and you get 3 times 2 equals 6. When p equals 3, 2 to the power of 3 minus 1 equals 7, which is also prime. Multiply it by 2 to the power of 2, which equals 4, and you get 7 times 4 equals 28. This formula still works today. In fact, all known perfect numbers come from it. Later, around the 100 AD, a philosopher named Nicomachus described perfect numbers in almost mystical terms. He said they represented harmony and completeness, while numbers that were too small or too large compared to their divisors were called deficient or excessive. So, from the very beginning, perfect numbers carried not just mathematical meaning, but also symbolic importance. During the Middle Ages and the Renaissance, mathematicians continued to search for new perfect numbers. Thinkers like Fermat and Descartes explored them and refined earlier ideas. By then, perfect numbers were not only seen as fascinating patterns, but also as stepping stones toward deeper number theory. As numbers grew larger, finding new perfect numbers became harder and harder. For centuries, mathematicians only knew about the first four: 6, 28, 496, and 8,128. It wasn't until the invention of modern computing that the search truly accelerated. Why? Because perfect numbers are directly connected to something called Mersenne primes, primes of the form 2 to the power of p minus 1. Every time a new Mersenne prime is discovered, it leads to a new perfect number through Euclid's formula. Today, this search has become a global effort. One of the largest projects is called GIMPS, the Great Internet Mersenne Prime Search. It's a distributed computing project where thousands of volunteers around the world donate spare computing power to test huge numbers. Thanks to this, mathematicians have discovered dozens of new perfect numbers. But here's the shocking part. Despite all this computing power, only about 50 perfect numbers are known, and each new one is unimaginably large. The most recent perfect numbers have millions of digits, so large that you couldn't even write them down in a lifetime. So, even with modern technology, perfect numbers remain rare and mysterious, challenging us to keep searching. Up to now, every perfect number ever discovered has been even. 6, 28, 496, 8,128, and even the massive ones with millions of digits. All of them are even, so mathematicians began to ask, could there be such a thing as an odd perfect number? This question has remained unsolved for centuries. If an odd perfect number exists, it would have to be unbelievably large. In fact, researchers have shown that it must be greater than 10 to the 22,000 power. That's a 1 followed by 2,200 zeros, far beyond what we can reasonably search by brute force. So, why are some numbers called perfect? Because they achieve a balance that almost no other numbers can. Their divisors add up to exactly the number itself. It's a rare harmony in mathematics where the whole equals the sum of its parts. But perfect numbers are more than just a curiosity. They connect simple arithmetic with prime numbers, binary patterns, geometry, and even the limits of modern computing. They have inspired philosophers in ancient times and continue to challenge mathematicians today. And perhaps most importantly, they remind us of something beautiful about mathematics. That from the simplest rules, like adding divisors, we can uncover patterns of incredible depth and mystery. Even after more than 2,000 years, perfect numbers still live up to their name. They're rare, elusive, and endlessly fascinating. And that's what makes them truly perfect.